Okay, so we're talking about equations of higher order. They're still higher order linear equations, but these are of the type that we're going to name non-homogeneous. We have spent a fair amount of time with homogeneous, where a fair amount of time of dealing with second order homogeneous equations with constant coefficients, right? So here we would like to start with non-homogeneous equations. We're going to write a few things here about notation. So we're going to assume that y is a function of x, and we want to consider a linear combination of derivatives of this function. In fact, derivatives of higher order. So we'd like to consider something that we would write as p sub j of x. Let me rewrite this. P sub j of x multiplying the jth order derivative of the function y. And so this would be from j equals 0 all the way through n. Okay, and so this left-hand side is a summation of derivatives, and this p of x is a function, a coefficient function. And so we're going to assume that this linear combination on the left-hand side equals a function of the independent variable. So if we're saying that y is a function of x, then the right-hand side is a function of the independent variable x. If we're saying that the state variable has some other name that's a function of t, then that right-hand side here would be a function of t. Okay, so this formulation, sum on the left equal to a function on the right, this is what we would call higher order linear ordinary differential equation. Or holiday. So you think of a better acronym, then by all means, holiday sounds like holiday almost, depending if I say it right. There's a factory in Knoxville called Good Golly Tamale. So I'm looking for some mathematical expression that I can name that reminds me of Good Golly Tamale, because I think that's a great name, and the tamales are quite delicious also. So higher order linear ordinary differential equation, where when we write that p sub j here, in fact, the very last one is going to be the p sub n of x is going to be assumed here to be exactly equal to 1. So it's not really a function of x. It's assumed to be a constant. So what this says is that when we expand that summation, the derivative with highest order will have coefficient 1. Okay? Now, I'm going to introduce some notation. So let's talk about some notation. We're going to define L. See, this looks like L of y is really two letters, right? But this whole thing is like a whole operator. That's what it is. L of y will be defined as that summation, the summation of p sub j of x times y to the j, okay? And here j running from 0 to n. So that right-hand side on the definition of holiday, the left-hand side, the summation on the left-hand side in that definition, we now are going to have a short notation, which is if the function that we're taking derivatives here is function y, y is the function that we are taking derivatives of, y to the jth, not the power, but the jth derivative operator. So that's the letter that we write here in front of the L. This L is for linear. It's a linear operator. It means it's a linear operator of higher order derivatives. So L, the way we define L here is as a linear combination of the derivatives of the function. With the understanding that the zeroth derivative of the function is the function itself. Zeroth derivative means you don't differentiate, right? So linear operator on y, defined this way, considers the linear combination of all derivatives of y from zeroth, which means no derivative, the function stays as is, up to order n, okay? So with this notation, maybe we write a few words. So here, Ly, you may think, well, it looks like li or lie. No, it's just say Ly, all right? So Ly denotes an operator and in this case, that operator is the operator of linear combinations of higher order derivatives. Higher order derivatives of y. That's what Ly denotes, okay?